Hello guys. Welcome back. Had a bit of technical chaos this morning because my iPad went down to 1% and it wasn't working. So hopefully everything will be okay. But I've had to piece this together very ad hoc. Right. I'm just gonna give you a black screen just while I do the register quick. Maths. All right. So today, yeah, things aren't as smooth as I wanted to today. I'm having to basically create this all on the spot. Oh, Ollie, you are here. Cool. I'll take you off in a second. Okay. Today we're looking at. Oh, actually, we wanted to start with that question, but it's not going to work. Let me just see if I can think my way around this. What is it? Start here. Okay, I think I can blag this. So we were going to start with basically a little summary question on everything we've done so far. So excuse the. Here's my iPad that has no battery left, and I can't depend on it. So this is what we were going to do. So yes, if you guys could start by having a think about this one today, that would be ideal. Cool. Give this a go, please. I'm gonna say that should probably take you about 5 minutes. A nice summary of everything we've done so far. As a hint, this is discrete data, so you're going to need to use all the rules that go along with discrete data. Cool. Give it a go. I'll give you 5 minutes to do that. Oh, and I'll resize the screen again because this iPad wasn't set up properly. There you are. Cool. So I'll start the timer now. 5 minutes. Make sure you comment, guys, if you need any help with this one. We will go through it in 3 minutes, though. Sorry guys, I just realised what that was about. The calculator was covering the chat there, Mike. Cool. So you guys are right so far though? So we've basically just typed everything into the calculator. I needed to make sure the only little problem I had there was I needed to make sure the frequency was set up to being 1 because it was trying to find the frequency in list 2, so I needed to tell it, well, the frequency is 1 for all of these. So it worked out our median and our quartiles. Okay. All right. So an outlier is an observation that falls either 1.5 times the interquartile range above the upper quartile or 1.5 times the interquartile range below the upper quartile, as we said the other day. I'm going to try and fit this window a bit better. As I said, a few technical difficulties today. Okay, cool. So, yeah, determine whether or not any data are outliers. So we need to do Q1 minus 1.5 times the IQR and Q3 plus 1.5 times the IQR. So let's work out the interquartile range. It's going to be 31, take 13. And then we can put that into our calculations. So we get 18 for that. So Q1, which is 13, take 1.5 lots of 18. And Q3, which is 31, plus 1.5 lots of 18. So my range has become 13 take 1.5 times 18. So I get minus 14 there. So there's not going to be a lower outlier. And 31 plus 1.5 lots of 18, which is 58. Cool. So looking through this, I don't think we're going to have any outliers. If you guys can see that. So looking at our data, no, nothing below 4 minus 14, nothing above 58. So no outliers. Cool. All right, next part. On graph paper, draw a box plot. So I can bring up some graph paper. Let's. This is a nice one, let me. Show your scale clearly. So we're doing show scale. Okay, so our data goes from, well, the lowest I can see is 5, the greatest is 42. So let's start my scale at 0, and we want to go up to, will that show up? Just. Does that show up for you guys as well? No. Okay, oh, it kind of does. You can just about see that. Okay, so there we go, 0, and we're going up to 42, so I need to go up in, I don't know, what should we say? How many have we got? Let's go up in 2s, so 10, 20, 30, 40. Cool. You guys have got slightly different, yeah, those are fine, yeah, cool. Yeah, everyone's in agreement so far, good. Alright, so putting this data onto my box plot, my lowest value was 5, so that would be 2, 4, 5 would be about here. So that's where my data begins. My lower quartile is 13, so if that's 12, 13 will be here. Median is 20, so that goes there. Up quartile 31. And my highest value was 42. So there we go. That's what your box plot should look like for this one. Cool. Hopefully that's okay. All right, moving on to what we're doing today then. So we're looking at something called correlation and regression, which I don't think you guys will have done before. Let's wait for this to load up. Cool. All right. So if you want to put title as correlation and regression. Okay. Sorry, just waiting for the broken iPad to load up. Okay, here we go. There we are. So correlation regression. We're now talking about two variable statistics. Everything we've done so far was one variable, and when we did it on the calculator, we type in x. We'd have our frequency column, but only one thing and one set of frequencies. Now we're going to be looking at two variable statistics. What we mean is there's two bits of interesting data. We're saying as this happens, maybe this causes this to happen. Don't know. So two sets of data that we suspect have some kind of link between them. So we're going to call these x and y. So when we do all this kind of stats, we need to be using the table on a calculator. We need to tell it that we've got x and we have y as well now. And if you're doing it on the class Wiz, you need. I'll show you how to do it in a second. So I'm going to give you the definitions of these words first, and then we're going to kind of look at them for the next couple lectures. So correlation. Let's do this in text. Correlation is basically a measure of the linear relationship between two variables. Well, let's say it describes it actually. Describes the linear relationship between two. Relationship between two variables. Cool. So it's basically a measure that tells you, well, do these variables have a linear relationship? Can we plot a line on a scatter graph that kind of describes them? And regression is basically the line of best fit. Solid finger, but it's a more mathematical way of finding a line of best fit. So those are our two topics we're looking at for the next couple of weeks. And we're going to start with correlation, because if two variables aren't correlated, we can't plot a line of best fit. It doesn't make sense. So I like to think there's 5 major types of correlation. So if you guys could draw 5 sets of axes. First one, we're going to say R is 1. So R is what we call the PMCC, which stands for, I'm going to get this wrong now, Pearson's product moment. It's a long one. Correlation coefficient. So you can see why we use an acronym. Pearson's product moment correlation coefficient. Okay, really it's just R. So there we go, and that is R, sometimes called the PMCC for obvious reasons. And it's just a number between -1 and 1 that tells you how correlated something is. So for some data that's got R equals 1, we'd expect data that pretty much follows a straight line. So get out of the way. So you can see, yeah, we got data, very linear kind of data. Okay, so then R might decrease. We might get R as 0.5. So we're still talking about a positive correlation because it's greater than 0, but it's not as close to 1. It's much more wavy. So we've got, you can kind of see a line in there. It's kind of got a trend, but it's a bit, bit messy. R is 0 would be no correlation. So random. You can't draw a line in there. A line wouldn't make any sense. R is minus 0.5 would be something like that maybe. So kind of negative trend, but nothing really clear. And then R is minus 1 would be perfect negative correlation. Oh, I've even drawn a line there at the bottom. Where your data really looks like a straight line. So it's a measure of not only how much it resembles a line, so the closer R is to 1 or minus 1, the closer it's a perfect line. It also tells you if it's positive or negative, positive gradient or negative gradient, depending on the sign. Cool. So that's what we mean by R. All right. So we need to define some variables so we can talk about the next bit. So there are two types of variables. You guys should have done this back at school. We have X on the x-axis, which is the independent variable, and Y on the y-axis, which is the dependent variable. Okay, these have a couple other names as well. So the independent variable, we might call it the explanatory variable. Because it explains this variable. What X does dictates what Y does. So this causes this to change. And because of that, we might call Y the response variable. So dependent, independent, or response explanatory, but X causes Y to change. And that's, again, in maths, that's what we always expect. That's why in functions, we do f of x, because its function depends on what you put in. Function depends on x. So x is always the thing we find interesting. We put x in to find y because it's the independent variable. You put a number in and you turn it into something else. Cool. So this assumes that one causes the other to change. But it's not always, we can't always take it for granted. So my question is, if variables are correlated, are they causal? But you can't see that because I've written it too far up the top. So if variables are correlated, are they causal? And what I mean by that is if I've got some data, so there's not much room on this iPad today. If I'll do it on these axes here. So let's say we plotted, I don't know, hours spent on Netflix against London Stock Exchange. London stock value. And let's say it did this. Maybe you would start thinking, oh my God, I can dictate stocks depending on how many hours I watch Netflix. They're correlated. You can't deny that they're correlated, but are they causal? Does one actually cause the other, or does the data just look like that? So you got to be careful. And there's a really nice website. I'm just going to find this one a sec. Be right back. Cool. All right. So we've got this lovely website that plots variables for you. So here we've got the number of people who drowned falling into a swimming pool and how it correlates with the number of films Nicolas Cage appeared in. And if we scroll down, we can see that the Pearson's product moment correlation coefficient is 0.6. So it's relatively strong correlation between people drowning in pools and number of Nicolas Cage films. This is only up to 2009. I'm not sure if this is still happening. If we scroll down, there's a few more of these. Oh, what have I done? Go back. The US spending on space science technology correlates really strongly with the number of suicides by hanging, strangulation, and suffocation. So that has an R of 0.992. So extremely strong correlation. Per capita consumption of cheese. So how much cheese eat in the US correlates to people who died by becoming tangled in their bed sheets, and that's got a correlation of 0.9 as well. So again, very strong correlation there. Divorce rate and margarine, again 0.99, so almost perfect correlation in that one as well. Yeah, so these variables, some of them, some weird and wonderful statistics, have very strong correlation. Honeybees and arrest for marijuana, almost complete negative correlation. So more bees is less arrests in that case. Sour cream and motorbike. Some of these are new. This is good. Yeah, so it's worth having a look on this website. If you just Google spurious correlations, um, there's some interesting statistics here, to say the least. So the point of this is that correlation, let's write this one nice and big. Correlation does not imply causation. Just because two things are correlated, it doesn't mean they're causal. One might not have caused the other. They might have perfect correlation, but it doesn't tell you anything more than that their numbers have a relationship. It doesn't say one caused the other to happen. Okay, so that's correlation in a nutshell. We will spend some more time on this in a minute, but we're going to talk about regression for a bit now. So linear regression. As I said earlier, it's basically the line of best fit. But we can't just, as you would have done at school. So if back at GCSE, you probably got a ruler out and you were like, maybe that's it. And then you would have moved the ruler around and said, no, maybe let's try this one. And you adjust the ruler on the page until you're happy with it. But it's not very mathematical. That won't hold up. It won't get you a mathematical equation. It's just, it looks nice on a graph. The way we do it is it's called, the real name of linear regression is it's the least squares regression line. And the linear regression line is the line that minimizes the average distance from the line. So if I draw a random line, this wouldn't be the line of best fit, but if I just draw this one. If we worked out the distance from each data point to the line, like this, if we added all those distances together, so we got D1, D2, D3, D4, D5. If I add all those up, so we get sum of di. Problem is here, some will be positive, some will be negative. The ones above will be positive, the ones below will be negative. So if we square them and sum them, we can find the sum of the distances from our line of best fit. If we minimize that sum, that's our regression line. So we call it the least squares regression line because we're trying to minimize this sum to get the perfect fitting line. So minimize this sum. And the way we do that is with our variance. We don't need to actually go into depth on how it does it. The calculator does all of this for you. But just so you guys know where it comes from, the calculator works out the variance of the x's, variance of the y's, and from having those two spreads, it can work out what the best line is that goes between those two spreads. Okay, so when we work it out, we're going to get an equation that looks like this. Cool. Which just looks like a straight line. So for every value of x, y changes by a factor of b, which is just the definition of a gradient. And this is just a straight line. So a would be our initial value, b would be our gradient. For every x you increase, y will change by that factor of b. If you've got positive correlation, b will be positive because you've got positive gradient. If you got, well, mirror image here. There you go. If you've got positive correlation, your b will be positive. If you've got negative correlation, your b will be negative because we're talking about gradients. Cool. Everyone happy with what we're doing so far? So we're talking about line of best fit, x, y. It will be y equals a. Gradient will be b and x. It's just an equation of a line. Okay, we call this the line y on x because y depends on x. And remember, this was our dependent variable. This was our independent variable. So when you're doing this, you have to decide which variable belongs on the x-axis. The x one is the one that's causing the change. If you don't think either are causing the change, it doesn't matter. But we ought to have on the x-axis the variable we suspect is causing the other one to change. Okay, and this is, if you did it the other way around, you'd get a completely different line. So we need to say that different to x on y, which would be the other way around. It wouldn't give you quite the same results. Cool. Right, so we're going to have a look at this then using our calculator. So I think I'm going to make up some data. Yeah, so bring up the calc. So we're going to go to our list. If you're on a class Weds, or actually if you're on the graphical, go to this list. If you're on the class Weds, I'll really quickly show you how we're going to access all this stuff. So if you're on the class Weds, go to menu, go to stats, and then instead of choosing one variable, we're now talking about two variables, which is the second one, y equals a plus bx, which looks like a regression line, so that's why we're choosing it. So choose that one, and you get x, y, and the frequency. We're never going to use the frequency, it should always fill in automatically. So if I try putting some values in, it puts them in as 1. We do want to change y though, so put in some values. So we're going to make up some data. Can I show you both at the same time? That would be pretty clever if I did. Cool. On the graphical then, oh god, that's confusing. We're going to type in our data. So let's go for, I don't know, let's go 1, 2, 3, 4 for x. And delete anything else that you've already got there. So on this one, one, 2, 3, 4. For y, we're going to do, I don't know, 50, 200, 600, 1000. So 50, 200, 600, 1000. Which is roughly linear, but shouldn't be too far off. Okay, I'm going to put down the class Wiz now because I actually want to draw this so you guys can see what's going on. So if you are using the class Wiz, at this point you would just hit equals. Sorry, you wouldn't. You'd hit equals and it'd go back to the main screen. Then you could go option and then regression calculation. On the class Wiz, we can go to var. Well, actually, let's set it up first. We need to tell it that we're now using two variables. So we need to put x list in list 1, y list in list 2, and tell it the frequency is 1. Then we're going to go to reg, which means regression. And we're regressing for x. And you can choose ax plus b or a plus bx. It doesn't really matter. I normally choose a plus bx. I think that's what they have on the class Wiz as well. And you get this selection of data in front of you. And this should be the same one. Oh, actually, it's not. What have I typed in wrong? That should be 600. Okay, try that again. A plus bx. There we go. So what this is telling me is that my a and b, so a is minus 350, b is 325, and r is 0.98. So this has told me not only my correlation, but also my regression equation. So my correlation for this data, thanks Callum, I didn't see that, but yeah, cheers. Yeah, my correlation is 0.98. So first of all, I have strong positive correlation. Which is good. If it was weak data, weak correlation, there would be no point plotting a line of best fit because it wouldn't be linear data. So remember, this is a test of how linear your data is. So because it's strong, it's almost 1. We know it's definitely linear data. So because it's definitely linear data, it makes sense to find a line of best fit. Okay, so because we know it's linear, let's use our other bits we found. So we have, I think we said y equals a plus bx. So my equation for the line of best fit is y equals minus 350 plus 325x. Which would be a line of best fit for my data. So you can do all of this stuff on the calculator. Okay, so only for linear data, and you have to do this first. You can't just randomly find a line of best fit unless you first of all check out R and make sure that it's strong positive or strong negative. Okay, has to be a strong value. Which I guess strong, I'd go from like 0.75 and upwards. Anything over 0.75 I'd say is strongly correlated. Anything less than that and it's starting to look like it might not be linear. Okay, so with our equation, y equals minus 350 plus 325x. With this, I could predict some things. So I could find y when x equals 7. So I could put 7 in and get y equals minus 350 plus 325 times 7. Which I will just do. And you should get 1925 for that. Cool, so we can use it to predict. There are some rules about this as well, though. So you're allowed to predict when the thing you're trying to put in, so y is 7, is in the range of your data. So if I bring the calculator back up, my data started, actually, I'm telling a lie. My data started with 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4. Oh, sorry, I've used a bad example there. So I've used 7. 7 was not in my range of data. 7 is outside. My data goes from 1 to 4. So if I drew my graph, 3, 2, 1, I worked out these data points. That's all I know, and that's the line I've worked out. Now, because I'm asking my equation to work out what's going on at 7, I'm assuming that the line keeps going like this. But that's a bit of an assumption. So when we do that, when we make an estimate that's outside of our range of data, we call this extrapolation. And extrapolation is unreliable. Because you don't know what's going to happen. We don't know what's happening after x equals 4. If, however, I asked it to calculate find y when x equals 3.5, that's within our data. So that would probably give me a good estimate because we know, yeah, it's probably going to be on that line still at that point, and we call this interpolation, which you should recognize back from when we're finding the median. So when we're finding the median or the quartiles, we were interpolating within our data. We were in one of our class widths trying to find our values. So because of that, it was a reliable estimate. So interpolation is reliable as it is in the scope of the data. Cool. So those are your two different types of estimation: interpolation, extrapolation. You put it both in the same, but one's unreliable, the red one, one's reliable, the yellow one. Cool. The other thing you can't do is we cannot use y to predict x because y was our dependent variable, x was our independent variable. You can't just switch them around. You can't use the same equation. If I wanted to do that, I'll show you what will happen. If I bring the calculator back up, so our equation, if I do this again quickly, go to a plus bx, we got y equals minus 350 plus 325x. Cool. If I go back, and I would never recommend you do this, but if I set my calculator up the wrong way around, so if I tell it x is in list 2, y is in list 1, I think I did that. Nope. Y is in list 1. And do it again, you can see that we get a completely different equation. So we get y equals, or even, let's rearrange it, it'll be x equals. We get a completely different equation, and it's not the same thing you'd get if you rearranged. It's just a horrible, horrible equation. So you can't use the y on x equation to predict x for y, but you could do it the other way around and then use this equation. But yeah, so normally if you're asked, you can always predict x, you can always predict y when you know x, but you can't predict x if you know y because that's not how our variables line up. Cool. All right, I'm very aware I'm doing a lot of talking today. We need to do some actual questions. So we're going to try a question. Annoyingly, this is on the other iPad. What's our battery like? 9%. Let's risk it. Why not? Cool. So I'm going to change iPads quickly, and hopefully this will still work. Fingers crossed. Is it going to work? Come on. Yes. We've done it. Brilliant. Cool. Okay. So this is a different size screen. So let's change this around. Right. So I'd like you guys to try this one. So it's giving you the total rainfall. Just try and get this fit properly. There we go. Cool. So it's giving you the total rainfall and sunshine in Camborne, which is nice that they're including Cornwall. So first of all, we're going to state the meaning of TR, calculate PMCC, and then decide whether a linear regression model is suitable. So some nice easy stuff. 5 marks, so I'll give you guys 5 minutes. So let's set the timer up now. Cool. So 5 minutes, we will go through this one. Cool. All right. Let's try and get through this then. Okay. So first of all, state the meaning of TR in the table above. So TR stands for trace. Ah, I'm on a different iPad now. Sorry guys, 2 seconds. Which one is it? Cool. Here we are. Okay, so TR means trace, which means there's hardly any rainfall. So I think it was less than 0.5 millimeters. So rounds to 0. So trace amount, small amount of rainfall. Okay, B, calculate the product moment correlation coefficient. Okay, so we're going to type this into our calculator. And it says also state clearly how you deal with the TR values. So if I bring up the calc again, we'll type our data in. No, come on, calculator. Okay, so X, we've got 2.2. Trace, we're going to put in as 0 because it will round to 0. 1.4, 4.4, trace again 0, 0.2, and then 0.6. And sunshine, 5.2, 7.7, 5.6, 0.3, 5.1, 0.1, 8.9. Oops, 8.9. It's always worth checking your data with these. I think the version of the calculator I have is a bit stickier. Okay, so we're going to type this one out. So a plus bx gives me r, so r equals 0.2. Sorry guys. Anyway, r is 0.234. Hopefully this will come back now. Yeah, there we go. 0.234, but it's too big again. Damn technical difficulties. Make sure you charge your iPads. Cool. So I would describe R as being a weak correlation. So yeah, we've got state clearly how we dealt with R. So we said TR was about 0. With reference to part B, comment on suitability of linear regression model. So it has a weak positive. You can even say it's got almost no correlation. So therefore it's not suitable for a linear regression model. Weak positive, no correlation, not suitable. Cool. Okay, let's try another one, providing the iPad stays alive. So table shows a chemical reaction and the amount of dry residue produced in grams. Cool. I'll try and size this up a little. So data is coded. So first of all, once you decode it, and then so given the data can be modeled by an equation of that form, which is an exponential, find the value of AB. So this is going to link to the log to linear form stuff we did back in pure maths. So think about logs. Find your x equals t and your y equals log d. And then we're going to try and fit them into that equation. Give that a go. We'll come back to this in 4 minutes and see how you guys have done. So 4 minutes starting from now. Need any help at all? Remember, type in the comments if you do. Cool. Right, let's talk through this one then. So, given that data can be modeled by an equation in that form, find A and B. So, what we need to do is turn this equation into a line equation. And the way we do that is by taking logarithms of both sides. So we get log D equals log AB to the T. So log D equals log A plus log B to the T. And we can use the power rule to bring the T down. So we end up getting log D equals log A plus T log B. Cool. Okay, so we need to find A and B. So I need to compare my log equation to my line equation. So we can see the bit with no x's in it is there. T is our x, as it says here. So that number is going to be equal to this bit. So log A is minus 0.635, and log B is 0.0334. So just by comparing them, I can come up with these equations. So I'm going to try and solve these. Remember, log on its own is log base 10. So I'll do 10 to the power of this to get A, and I'll do 10 to the power of the other one to get B. So 10 to the power of minus 0.635 gives me A equals 0.232. And 10 to the power of 0.0334 gives me B is 1.08. Cool. All right, explain why this model is not reliable for estimating the amount of dry residue produced when the temperature is 151. Well, if you look, our table only goes up to 94. If I bring this back down again, table only goes up to 94. 151 is outside of the bounds of our investigation. So we can say extrapolation. Data goes up to 94, and we say 151 is outside of our investigation. Cool. Anyone got any questions on this? Everyone okay? Cool. All right, last question today is going to be, well, we'll see if it's, I think it's the last one I planned for. Nope. Nope, two more. All right, let's try these two then. So here's one based on data from Perth. This one should be a little bit easier. So if you guys could try this one. Yeah, so 3 marks. I'm going to pause for 3 minutes. Um, Please comment if you need help. I'm not hearing much from you guys today. I'm worried the stream is lagging. Yeah, it does look a bit choppy. Can you guys post me something in case this is a bit choppy? I don't know what's going on. Things just aren't working today. Cool. Right, let's start timing now. Let's see what's happening. Okay, yeah, that's what I was worried about, Billy. Let me know if it's improving. I've tried to increase the buffer rate, but I think it's something to do with resolution. I don't know, basically. Sorry, guys. Right, sorry guys, I don't know why we're so laggy today. I will try and work this out. I think it might be because I upscaled the size of the screen because the iPad broke earlier. Oh, this day is a catastrophe for streaming. I'm gonna go through this as normal. It might be worth rewatching this because, as you say, it's quite choppy. Yeah. All right, let's go through this and just see what happens. We only got 15 minutes left, and hopefully you guys can rewatch this. I am sorry though. Yeah, I'll try and scale it down or something to make things work better. Right, calculate the PMCC for this data. So if we bring up the calculator, so we've got 18. Oh yeah, we need to decide which is which. So as Callum said, how do you decide which is which? So we need to decide which of these variables are going to affect the other. So we've got air temperature and rainfall. Interesting. Do you think temperature makes it rain or rain makes the temperature change? So I reckon the temperature would be what causes the rainfall amount to change. I think the hotter it is, it's the air temperature. So if humidity's got something to do with it, or you might have, if there's no clouds, there's no rain, the temperature will rise. So, or we could say rainfall. Ooh, yeah, I think let's go rainfall and temperature. I think. Yeah, so we'll go rainfall as our x. No, I'm going to second guess that and do it the other way around. I think you could argue it with both, but I think they normally put X in the top anyway. So I think normally T will be on top. So yeah, temperature and top. And then we got 3, 13, 4.6, 32, 28, 63, and 22. No, what have I done? Missed out a data point. 18, 16.4, 15.3, 15, 13.7, 10.2, 12. Okay, there we go. So a plus bx. Okay, so r is minus 0.8. Negative 3. Okay. Reference model. Could we use a line for this data? Yeah, it looks like we could. It's got strong negative. So yes. Cool. If you had done it the other way around, I think you'd still get decent correlation. So I think they'd let you have it either way around for this one. So if I go back, setup, my list will swap around anyway. This one, list 2, and regression x. Yeah, I still get minus 0.83, so that's good. Yeah, cool. So it wouldn't matter which way you did it. Okay, last question for today then. 10 minutes to do it. Could you guys give this one a go? So it's another logarithmic one, so be careful, but should be okay. So give this a try, and in 5 minutes we'll go through this one. It's worth a bit more marks than that, but I'd like to get this done before the end of the lecture, especially as I know things are lagging. So let's say 5 minutes for that one. Cool. Comment if you need any help.